All right, thank you very much. If you see my name and it's kind of difficult to pronounce or it looks like it's a big challenge, don't worry. It's Ukrainian. You just say it like the fish, Pyrcz, and you get an A for that, 100% for that. So, acknowledgements. We all stand on the shoulders of giants, and none more so than professors. I found that out in the last 6 years. I'm going to cite student research all the way through this, and so I list some of the graduate students that I've worked with over my 6 years at the University of Texas at Austin, and so those students are up there. Also really happy and excited to be able to collaborate with other professors or faculty. We actually do work together, which is really nice, and so I list some of the professors I worked with there. But first and foremost, I really do want to thank the organizing committee, specifically Professors Eidsvik and Elif Moore for their invitations to give this talk and their assistance. Seems like technically I'm a little bit challenged. Even last night I was having trouble uploading the file, but I got it done. So we're here, we're ready to go, and I do appreciate your patience with me. I want to acknowledge the IAMG. I've heard people say it before. I think Jennifer said it yesterday, that I really felt like I grew up in the IAMG. All my earliest conferences, publications, and so forth, and the mentoring, always members of the IAMG. And so I'm just so happy to be part of this community. And as I've given this talk and attending this conference, I'm looking around, I'm seeing all the graduate students here. And I see myself in your role. I see myself in your place. And I'm really happy to be now able to support the community in many ways. My motivation, I really feel like the subsurface needs new capabilities to be able to model. A lot of people are trying to grab machine learning, data analytics technology off the shelf and apply it to the subsurface. And I feel in many ways that we're unique. And so I think there's a great opportunity to try to update, to do research, improve these methodologies. Also, I'm really proud. I think us, the geostatisticians and those who work in geostatistics, are uniquely situated to take on challenges with data science and machine learning. In fact, I will probably bridge over to boastfulness during my talk when I talk about all of our great opportunities, we as experts. And also, I think there's a lot of opportunities for us to make new adaptations and research to see machine learning and data analytics through a geostatistical lens that will allow us to see all kinds of great new opportunities. Okay, what I'm going to do during this talk is I'm going to go ahead and talk about data analytics and machine learning. I'll start off there. It's an introductory type of discussion to you who are new in the field. It'll be a useful introduction. To you who are experts, maybe you want to use the slides. Maybe it'll be a useful communication tool that you can use to demystify it to others. Then what I'll do is I'll talk specifically about subsurface challenges. I guess since it's a keynote talk, I can get a little bit philosophical. I can talk about some ideas or perspectives as far as the future goes and how we're unique and different. And then from there, I'm going to jump in and do rapid fire, a whole bunch of different examples to back up and prove that we are uniquely situated and we have some really great challenges we can work on. Okay, first of all, do you work with big data? Show of hands, who works with big data? Oh, I see all those hands go up. I saw a couple of people, but both hands up. That's awesome. That's a lot of big data going on there. And I got to tell you, how do you know if you have big data? Well, you can look up on Google and you'll find that there's the V's, the criteria for big data. Volume, velocity, variety, variability, and veracity. Volume. Do you have data that's large and difficult to handle, difficult to visualize? Maybe it doesn't even fit on your hard drive. Check the box, you have volume, you meet that criteria, you're well on your way to big data. What about velocity? I have to confess, the tech people are a little bit snobby when it comes to this. They think velocity means real time. It must be real-time data feeding into your model. I don't agree with that. I say if it is high rate of collection, continuous relative to your decision-making cycles, that's good enough. What am I talking about? I worked in oil and gas for a while. We were always running to keep ahead of the bit. We always had new data coming in, and the complexity of our workflows, how do we incorporate that new seismic, how do we incorporate those new well logs, was challenging enough that we were always challenged with velocity. Check that box, we have velocity. Variety, do I need to say anything? In fact, how many people here have already been talking about pore space, mineralization, diagenetic alterations, and then I've heard people talking about basin scale analysis, trying to look at entire basins at the same time. Check that box, we all get that. And the geosciences, definitely. Variability. Do you work with data that changes during the project? The acquisition changes. Anybody here worked with seismic? Exploration seismic. 2D exploration lines, 3D. Next thing you know, they put some ocean bottom nodes in, melt the butter, pop the popcorn, you're watching the movie. You can see this hardening behavior as the water is replacing the oil in the reservoir. It's amazing how our data changes over time. Check that box, we also have variability. And veracity. Do we have any subsurface data that has perfect certainty? I'm looking. Who has that confident look on their face? I'm not seeing it. I had some students, some years in my undergrad class, they'll put up their hand and they think they got me. They'll say production data. You can measure that. It's coming out of the ground. Is that certain? Where did it come from? We commingle our production. We don't understand fully with the heterogeneity in the subsurface exactly where it's coming from. Clearly soft data, check the box. Any doubt, we get an A for big data. In fact, I say the subsurface has been big data long before tech companies even learned what big data was. Am I correct? I'll tell you what, I visited Google and said that. I told them they need to listen to us more than they're talking, because we know something about working with big data in the subsurface. What about statistics and data analytics? Anybody kind of, I don't know, just confounded with this use of terminology? Statistics, what is it? About collecting, organizing, describing, interpreting data, drawing conclusions, supporting decisions. I tell my students, if you don't impact the decision, you don't add value. Is that rude? I try to be a polite Canadian. But every time I look up data analytics online, what I find is some discussion about data visualization, supporting decision-making, building models. And you know what I realize? Statistics is data analytics is statistics. If you work in statistics at your job, update your CV. Data analytics is such a hot topic right now, it sounds really cool. What about machine learning? I did what everybody does. I Google searched and I got the Wikipedia page and I put in my PowerPoint slides. My apologies, but I think it's a useful definition from the community. First of all, a study of algorithms or mathematical models. It's a toolkit. It's multiple models. You got them together. Now what do? The computer systems used to progressively improve their performance on a specific task. Okay, they're models, a toolkit that's learning. How are they learning? They build a mathematical model of sample data known as training data. They're learning from training data without explicitly being programmed to perform the task. I apologize, this is a definition that's used to ad nauseam. It is the basic definition. Everybody stops there. They stop reading the article, they got what they came for. But if you read right to the end of the article, you'll find this little nugget of truth, excuse the pun, in this community. Where it is infeasible to develop an algorithm of specific instructions for performing the task. What does that mean? I was in a PhD defense, and for the nth time, the easy question was asked. Why didn't you use machine learning? Why did you do all that engineering physics? And that was it. Dr. Torres Verdin had enough. He just stood up, and he was the advisor, and he stood up and he defended the student by saying, don't jump to data-driven methodologies as a crutch instead of understanding the beauty of the natural setting. That was poetic. I thought that was a great way to describe it, and that sticks with me even to today. Let's not jump at these methodologies without understanding the physics, understanding the geology, understanding the beauty behind it. Do you work with deep learning? Do you work with convolutional neural nets, recurrent neural nets? Are you building GANs? I don't care what you do in machine learning, this equation from now on, I curse you that it will come to your mind. Every time you build your model, you'll remember that you're simply building a model that takes inputs and maps them to an output. It's a very simple model, in fact. The inputs are called predictor features. Now, I see some folks out there, I'm sure we have some old school statisticians, and for you, I dedicate the terminology, the independent variables, right? And then we have the outputs, the Ys. That's known as the response feature or features. There may be more than one. And the old school statistician called that the dependent variable or variables. That's what our models are all about. It's just an equation like this, and we'll understand that there's some error term, and there's a whole list of assumptions that we make, the fine print of our models that we need to be careful with. Actually, a shout out to Hastie and all, James and all, the famous books in machine learning, Applications in R, and The Elements of, in which they use the term statistical learning, which I think that's a great idea because it reminds us of what it is. It's a statistical model. It's not some magical machine that can figure everything out for us. As I proceed with this talk, you're going to see, I'm going to show you many cases in which the machine can fail, in which case the machine is just a simple statistical model. Have you ever built a predictive machine learning model? I'm looking around. I see some nodding. I see some smiling. Thank you very much. Appreciate that. This is my one-pager on how to build a predictive machine learning model. This is the entire workflow right here. Now, it's very interesting because I'm demonstrating a cross-validation, a test-train workflow. Now, there's people here who are a little bit more purist. They use a train, validate, and test workflow. For you, I apologize. I've simplified this for version 1.0. Now, how does it work? What you're going to do is you're going to take the data. That's shown right here. Now, what we have is a very simple data set. Our predictor feature, recall the definition, is simply going to be Z. Oh, excuse my Canadian, Z. And the Z right here, elevation. And we're trying to predict permeability. So we have some type of depth-based trend we're trying to model a machine learning model. What we do is we take our data and we split it into two pieces. We have the X's are the training data, the solid circles are the testing data. Now, does everybody here have a location in your office where you have a dusty pile of papers and you haven't gone there for a long time? I like to call it the low-energy sedimentary environment in my office. Okay, you do. I see you smiling. I know you have exactly what I have. It's all of us, right? You take that testing data and you put it in that pile. Now, you're not allowed to look at it. Don't peek. You put the testing data in that pile and you start working. What you're going to do is you're going to take those X's, and can you think of the world's most simple machine learning model? What would that be? Oh, that's awesome. Everyone's getting A's. Seriously, linear regression. Thank you very much, Professor. You take a linear regression model and you train the parameters, the B1 and the B0, the intercept term and the slope, to your training data, and you get the very best possible fit. That's training model parameters. That's that solid line right there. I moved it around. I'm showing you I'm training. This is a multimedia extravaganza now. So then what you do is, what's the next most complicated model after linear regression? Well, linear regression is really just a first-order polynomial model. You could do a second order, a third order. There you go. There's your third-order polynomial model right there. You train the model parameters. Now you have 4 of them, and you train them to the training data. And then what you do is you do fifth order, seventh order, increasing complexity going down. Next, what do? Do you remember where you put that testing data? Are you like me, that when you decide to put something where you'll never forget where it was and you're keeping it safe, that then the next day you forgot where it was and you're playing hide and go seek with yourself? Okay, please, nobody's supporting me. I'm by myself in this. Okay, so we didn't do that. We found the testing data. Let's go ahead and bring the testing data back in. And now what we do is we look at the model and we see how the testing data is performing. It was withheld from training the model. It had nothing to do with the training the model parameters, the fit of the model, and you score each of the models. How did it perform with the withheld testing data? What is that? It's a dress rehearsal. You're trying to mimic the process of using the model to make prediction, because I don't care how my model performs at data used to make the model. Can we agree? Do we make money by predicting? Kriging has exactitude. It just gives you back the data values. We need more than that. So we go ahead and we check our models and we find out which one performed best. First, third, fifth, seventh. The third order polynomial model had the best score. It performed best with withheld testing data. We're going to go ahead and, after all of that work, do you feel tired? That was a lot of effort, right? We built all those models. We ran all those tests. All that we got at this point right here in our workflow is 3. What is that? It's a tuned hyperparameter. It's the right level of complexity from the dress rehearsal that tells us the very best model we can build is this one right here. Now, what do? We take all of our data and we retrain that model. Because can you imagine if you made a model and it was wrong at the data locations? What's it cost to drill a well in deep water? Can you imagine if you were wrong at the well location? Anybody ever done that? Okay, nobody's going to put their hand up. Okay. So we can't do that. And so we'll go ahead and we'll use that hyperparameter and we'll get the best possible model. Now, I owe you a couple of definitions because I use some terms here. Model parameter. Model parameter just controls the fit of the model. And so the third order polynomial model has a B3, B2, B1, B0 term. It's just moving that function around. It's controlling the fit. Those are model parameters, and they are trained on the training data. Hyperparameters are totally different. Let's not mix them up. Just ask yourself the question, does it control the fit of the model, or does it control the complexity of the model, i.e., the flexibility of the model? In our case here, the choice of first order, third order, fifth order, seventh order, 13th order would be the hyperparameter here. Okay, so hyperparameters are tuned on the withheld testing data. What would happen if we went ahead and picked the complexity based on the fit with the training data? Which model would you pick? First, third, fifth, or seventh order model? Which one fits the training data the best? The most complicated model would always win. Do you see that? And that's why we have to do this. We would always be biased towards the most complicated model. How is that model doing at the withheld testing data? I owe an apology to the institution here. I've literally punched a hole in your floor with my model. I'm making a mess. Okay, what are we trying to do here? This whole hyperparameter tuning thing in machine learning is all about avoiding the evil overfit. What is overfit? Well, as we increase the complexity of our model from simple to complicated, the error in training will go down and eventually can actually get to zero. But what will happen with the withheld data, the testing data, the dress rehearsal, if you will actually go down and then come back up. In this region where training error is falling and testing error is climbing, that's the region of overfit. Here's an example of an overfit model right here. Look at the training data. Do you see how it's perfectly fit? Anybody ever read a paper, reviewed a paper, seen a paper where they say R-squared value of 99.9%? Perfectly fit model? Probably overfit and not tested appropriately. Here's an example of a more balanced model, may perform even better. Now, I have a confession to make. I do a lot of coding. Anybody else have that thing where you do little coding vacations? I mean like pretend you're on vacation and just go code. I mean like fill up your calendar with events that don't actually happen. Students, please don't pay attention. And then basically just go off in your office and make something cool. I actually do that. I make little interactive dashboards in Python. Because every time I find an area of teaching, an intellectual hurdle that students aren't quite getting, I like to make a little dashboard. But to save the stress of the organizers, I've simply taken screen captures of my dashboards and I show them here. I'm not running it live. But I promise you, go to my GitHub account and you will find hundreds and hundreds of these dashboards, teaching tools, and so forth. And I put them up on GitHub open so that people can use them. Okay, sorry, I'm not bragging here. I'm just saying you can go here to my GitHub account and get them. Repeatability. Here we go, I got a dashboard, I got a model. This is my data, this is my model. It's simple. Don't worry, it's supposed to be simple. This is the error distribution in train and test, and this is the different degrees of model complexity from first order polynomial to 12th order polynomial. The train curve is red, the test curve is blue, and because I'm a geostatistician, yes, I bootstrapped it. And since I bootstrapped it, I got a little bit of an envelope here that we can look at. Okay, everybody understand the dashboard? We're going to proceed with it. Okay, I'm going to zoom into the dashboard, and now you can see my data and my model. How am I doing? First order polynomial. I got my model order all the way down as low as it can be, and I have my first order polynomial right here, and I'm going to overfit my model. You're going to see something very catastrophic, dramatic happen here. We're going to increase the model order to order number 2. What's going to happen? Is the universe going to end? We're going to be okay? Order number 2, the error is decreased. Look at that. Everybody see that data set is very much in the shape of a parabola, second order, quadratic. It just fits it perfectly with a second order, right? Now everybody knows that if you increase model complexity, you'll cause overfit. I already said it, right? So let's go ahead. What do you think is going to happen if I increase it to a third order polynomial? Are the wheels going to fall off the wagon, as they say in Texas? Nothing happened. Okay, everybody's thinking, okay, maybe Pyrcz is lucky. It's not a big deal, right? Let's proceed one more time and see what's going to happen. Are things going to break? Fourth order polynomial, still good. Everything's fine, right? Okay, what I'm going to do now is going to jump all the way up to a 12th order polynomial. What's going to happen? Boom. You expecting it? 12th order polynomial. What happened? Everybody knows too complicated. It's going to get overfit. It's going to mess up, right? Now I have another dial here on the dashboard. If you look right here, do you see noise? I have a perfect parabola right now. I mean literally y equals x squared relationship right now. If I go ahead and I turn this dial up, I can add random noise at every data location. Now I promise you, I'm not doing anything big here. If you watch the data very carefully, you will barely see it move. 1% noise, get ready for it. You see what happened? What causes overfit? Too much complexity with noise in the data. If you have perfect data with no noise, you're not going to overfit. The problem is having a machine learning model that's too complicated, too flexible for its own good. It can start to fit the noise, the data idiosyncrasies, and that's the problem. Everybody good with that? Kind of fun, eh? I like these dashboards. They're really, really cool. Okay, so that's overfit. Complexity plus data noise, that's our issue. Okay, what did we learn? I promised you this was going to be a very basic introduction to machine learning, data analytics, and I think I delivered on that. It didn't get too complicated. What did we learn here? Data analytics is statistics, spatial data analytics is geostatistics, and I give credit to Professor Pyrcz from Stanford. What a cool guy. I was a brand new professor. We sat down. I said I was having some trouble with fundraising. He just put his arm around me. He said, Michael, just start calling it data analytics. You'll get funding. And that's exactly what happened, right? Okay. Machine learning is statistical learning, and James et al. And Hastie et al. I think we need to remember that statistical construction. Okay, so let's go ahead and talk specifically about subsurface data analytics. I think that's really important. Let's jump in. First of all, if nobody else has ever done this before, it is my great honor this morning to welcome you to the fourth paradigm of scientific discovery. Did you notice? Did you look out the window and the sky seemed bluer and the sun was brighter and everything was nice? Well, it is. Now, part of the problem is this. I say 2010, I would not fight back if you came up to me and said, we've been working with artificial neural nets since 1980s or something like that. I'm cool with that. Let's move that around. It's fine. What's the paradigms of scientific discovery? The first paradigm, doing experiments, empiricism, and then understanding our natural setting. In fact, we've been doing this forever. I don't really know where to put that date. All I know is that archaeologists are digging up skulls in Egyptian sites, and I'm glad I wasn't part of their medical experiments. What else do we have? We have, of course, the second paradigm, theoretical science. We learned that we could put the laws together. We could build the functions, understand the relationships. And then, of course, we got the computers, and we recognized we could do computational science simulation paradigm. What was that? The world is too complicated. Coupled physics, complicated geometries. We couldn't solve it analytically, so we put it in a computer and we simulated it. The fourth paradigm. It's funny, the fourth paradigm is really a natural progression. It's not that revolutionary. It's the idea that we have a lot of compute resources. We can go through large data sets. We can find patterns. We're hoping for artificial intelligence, or maybe not hoping for it. Depends how you feel about Skynet. All of these things. Now, what does it mean to work in the fourth paradigm of scientific discovery? I think this is really critical. We do not replace previous paradigms. What we do is we augment them. Those who work in the second paradigm, theoretical science, know that it's based on empiricism. And anybody here who works in computational science and simulation knows that, in fact, you're using both first and second paradigm in those models. I remember when we were doing transport of grains in turbidite systems into deep basins with computer models, we couldn't figure out from analytical expressions or laws the entrainment of grains from the bed of the sea. We had to use flume experiments and calibrate the numbers. That was first paradigm in our third paradigm methodologies. So we augment the new scientific with new scientific paradigms. We don't replace the old. I think we should be proud. I think geostatisticians and those who work in the subsurface can be really, really proud, because heterogeneous, sparsely sampled, vast systems with complicated physics and high-value decisions drove us to be the pioneers. We've always been data-driven. Think about the types of data sets we work with and the prediction problems we've been making for so many decades. We can go back to probability and stationary concepts, 1930s, from Kolmogorov. We can talk about Danny Krieg, volume variance relations, and making predictions in space. We can talk about Mathron coining the term geostatistics and also bringing mathematical morphology and putting all the theory on top of geostatistics in his beautiful work. Applications of oil and gas, some of the original open source software. Like, think about that. At a time where people really weren't doing that, we were getting into open source and people were sharing that around and developing new concepts. And of course, now we have machine learning. We have data analytics and all the stuff we're doing right now. You know what we said when object-based modeling came along? We said it's fine. It doesn't matter if it's not varigrams. If it does the job, it's part of the kit. It becomes part of our geostatistical toolbox. And I think just like machine learning right now, we see it as all being part of our toolbox, and there's a reason that we're leading. We are the original data-driven scientists. We have been big data long before tech even learned what big data was, as I said before. And because of that, we have much to share with our broader engineering and science community. I was invited to be a keynote speaker at an industrial engineering conference in America, and that's what I said. And it was amazing because they're looking down the road and they're wondering what will it be like. And I'm saying, talk to us, talk to the people on the subsurface. We've been doing it for a long time. But the subsurface is unique, very unique. In fact, we have sparse, uncertain data, complicated, heterogeneous, open Earth systems. You read the work of Oreskes and all. We cannot verify our subsurface systems. They're too complicated. They're too open. There's always those discontinuities. High degree of necessary geoscience and engineering, interpretation, and physics. There's a thick layer that's required. We can't just take the data and put it into the model. We can't replace the geoscientist and the engineer, and we have expensive, high-value decisions that must be supported. How much does it cost to drill a single well in the North Sea? I was recently presenting at an American company in Texas, and they gave me about $150 million to drill something new in deepwater Gulf of Mexico. We can't make mistakes. May I compare and contrast our uniqueness to a common and very successful application of machine learning, the recommender engine. Anybody here on Spotify? Anybody just let Spotify play and see what happens? I do that all the time. I let the recommender engine just go. Now, I am Canadian, and so I listen to a lot of Canadian music. And every once in a while, a song will come on. I'll be like, ooh, that's got a bit of a hook. I like the hard rock. I start bobbing my head. I go about 10, 20 seconds before I catch myself. I go, oh, darn, not again. And I fast forward as quickly as I can. Guess what it is? Nickelback. On behalf of all of Canada, I apologize for Nickelback. And I promise you that that is a case of the machine getting it to... Wait, some of you think I like Nickelback, right? Is it the long hair? You're looking at me and you think, this guy likes Nickelback. Okay. I promise you it's a case of the machine getting it perfectly wrong. What is the cost of being wrong for Spotify? I fast forward the song. I'm on Twitter. Do I start a Twitter tirade? Try to cancel Spotify? Do I do something like that? I just fast forward and go on with my day. What would be the alternative? Should I hire a DJ to sit in my faculty office all day long just spinning those songs for me? What do you think? Should I do that? If you're nodding, you grossly overestimate how much a professor in Texas is paid. I cannot afford to have somebody in my office just playing songs for me all day long. But I have to admit, Madej and Jose, wouldn't it be cool if you came to visit in my office and I had a DJ? Maybe people would come see me more often. All right. We have to develop novel subsurface data analytics and machine learning solutions that integrate geoscience and engineering. Everything is not like the recommender engine. Now, sometimes I get asked to go on panels and make statements. We'll even have a panel discussion on Thursday. I think it's going to be really exciting to see. But I have some biases, and let me be very clear about my biases. I think there's opportunities to do more with our data. Anybody here ever worked with subsurface data? Anybody here ever worked with subsurface data and somebody says, oh yeah, go talk to that person, they're the expert on the project, and you sit down with them and they say, I don't know where the data is. You ever had that happen? Or they opened up the data file and they say, so-and-so was working on it, I can't remember if this is the right version. You ever have that? Or the metadata. What's metadata? Data about data. And metadata is not there, so you don't know how the data was generated. You don't know what happened to it. Okay, I don't want to complain here too much, but I'm saying there's opportunities to do more of our data. My P10 outcome from this digital revolution is we just do a better job with data. I think there's opportunities to teach data analytics and machine learning to engineers and geoscientists. I've taught hundreds and hundreds of students in the university. I've taught over 2,000 working professionals in industry. And you know what? They're really good at it. They learn it very well. They're prepared for it. Geoscience knowledge, engineering knowledge remains core to everything we do in our business. Okay, what do we learn? I promised you I was going to have some basic introductory stuff. I'd get a little bit philosophical. I hope I reached my goal. We augment previous paradigms for scientific learning. Engineering and geoscience remains critical. The subsurface is unique. Nickelback. We need novel solutions. We in the subsurface may be further down the path, and we can share our knowledge with the rest of the community. I'm trying to look around here. I'm trying to see if there's any stares of hate, because I'm pretty sure there's going to be one or two Nickelback fans in here, or just like, you know, I used to like Pyrcz. Geostats guys seem real friendly on YouTube, but now that's it.
We're all going to look it up.
I should check the analytics. Maybe there'll be a spike of Nickelback in Norway. I'll be responsible for bringing Nickelback to Norway. I'm sorry. Have you ever heard the adage, garbage in, garbage out? I like to say bias in, bias out. I think that's a good way to describe it. You know what's really interesting? Let's look at the geostatistical subsurface modeling workflow. We love this workflow, don't we? It is so beautiful. It's like you gather the inferential step. You gather all of the data together, you formulate a subsurface framework, you bring all your knowledge of the geology and engineering together, you go ahead and you formulate histograms, ferrograms, correlations and covariance matrices and so forth. You put that all together with some trend models. Ooh, that's the subjective part of modeling, right? That trend model. You put it all together and you make geostatistical simulations, and you look at them and you check them against the input statistics. You apply a transfer function. What is a transfer function? Taking your models and getting them as close to dollars as possible to support decision making. That's what we do, right? Then what we do is we check and we make sure that everything was right. Biased inputs result in biased models result in biased decision making, and that's not good. That's a problem at work. We don't want to do that. Or do we have bias in our data? I went across domestic gas shale in the United States, and I looked at all of them. And when I looked at all of them, what did I find? I found that as I went across their distributions, I applied simply cell-based clustering carefully. And what I found was Haynesville, Barnett, Fayetteville, and so forth. I saw 4%, 5%, 8%. Sometimes I saw as high as 15% biased high in their estimation of gas production. Is that a problem? If you look at lookbacks in the industry, you'll find out that they find systematic overestimation of about 15 to 20%. Is this part of it? Biased data doing it? I think so. We have a variety of methods by which we can debias, and I think we're very good at this. I think this is part of what we can share with the world. And so we can take these methodologies, data weighting, distribution imputation. Does anybody do that stuff? That's what they call the soft data debiasing, where you use secondary features to help fill in the missing parts of the distribution. Is sample data bias an issue in machine learning models is the big question. What do you think? Are machine learning models just really intelligent and you feed in the data and they'll just take care of it? We did a check. Wendy Liu, one of my previous PhD students, we sat down together and we said, let's test that. We created a wide variety of data sets with a variety of levels of bias. Then what we did was we ran those models and we checked the results because we knew the truth. We had truth models and we could see how much bias in resulted in bias out. What did we find? they were still biased. Even if the training was biased, but the testing data was unbiased, that signal of bias was preserved in the model and came out in the model predictions. So what did we do? We had a very simple idea. Why don't we take our cell-based declustering weights and decluster the machine? What's the easiest machine to build? Tree-based machines are very easy to visualize and understand. This is a system for which we have two predictor features. We have our data right here. The color is going to be production. We got fraction of clay. We got porosity. We can go ahead and make predictions, pre-drill predictions of production of wells. What do we find? If we use the debiasing weights, these are regular decision trees right here. Here, the size of the dots are scaled to the data weights. And if you look really carefully, you're going to see differences. So what do we learn? Weighting the trees results in a different model. Okay, that's the first step. Then what did we do next? We looked at the degree of bias for unweighted trees, the red, and for weighted trees, the blue. What did we find? It worked pretty good. We saw a reduction in bias in the predictions from the model, and we found that it was adaptive. If there was just a little bit of bias in the tree, it was a little correction. If there was a lot of bias, we got much more correction. And so this was really exciting. We found that it was useful to do weighting, geostatistical methods that we know and love, to be able to go ahead and fix machine learning models. Can you apply this to every predictor, every type of prediction models in machine learning? Sure, you could do weighting with your models. Bias spatial data imposes a bias in machine learning models and must be integrated just like, or mitigated just like geostatistics. Do you all remember minimum acceptance criteria? That was a paper back in 2003. I thought that was a really cool paper. You ever had that feeling where you wish you could go on a time machine and write that paper before they did? Because it was such a great idea. It was such a simple idea. It was go ahead and check your models. Check the goodness of your geostatistical models by looking at, if you put it in the model, make sure it comes out of the model. Does that make sense? You close the loop. That's what they say in industry, close the loop. So you go ahead and you close that loop, you check your data exactitude, data at the data locations, histogram, variogram, correlation coefficients, and Deutsch in 1997 actually had a accuracy plot for checking the uncertainty model goodness. Go ahead and check all of those inputs in the model. It's a great idea. Boisvert and others looked at why don't we extend that to MPS and start checking other aspects of the model, such as the endpoint histogram, to see if you're getting the training image patterns back in the MPS simulations. What a great idea. That would be fantastic. Jose, did you get it? Okay. So minimum acceptance criteria, extend it to MPS. Okay, now we're building models using GANs. Anybody building subsurface models using GANs? I cite Lucas Moser as one of the originals. There's a bunch of other people who have been working in that field with GANs. GANs are awesome, aren't they? They really are cool. And so you can build these GAN-based models. And so one of my students was looking at minimum acceptance criteria for images. And I think it's a really good idea. And there's lots of ways that we can try to do this. But what does it look like? One thing you can do is you can take your training image, you can calculate locally variable proportions or statistics, the trends, and you can check to see what are you reproducing as far as those trends. Are you getting the trends from the training image back in the model? Do you want the trends? Was that an accident or was that a feature you wanted in the model? You can also go ahead and do what they were doing at Stanford for a while, where they're basically trying to visualize the uncertainty space using dimensionality reduction, i.e. multidimensional scaling or other methodologies. Here's a T-SNE approach right here, and you can start looking at the individual training images and the GAN-generated models and see where your images are relative to the models, i.e. their similarity. You can also do something very simple. You can look at the multiple realizations from GANs. GANs can take a latent vector and just generate new images. You ever see where they take a face, and they go ahead and morph between the faces and everything in between looks like a human face, but it was artificial? It's a fake. You ever see where they make people look like Tom Cruise? You seen those videos? These are all deep fakes, right? Well, we can go ahead and look at those, and we can see over all of them, do we have a reasonable space of uncertainty? And the answer is no. It looks weird, doesn't it? It's not really. It's conditioning in ways that we didn't expect it to condition. It may not be exploring uncertainty too well. Okay, so we want to extend these ideas of minimum acceptance criteria into our deep learning models. Our models are used to support expensive decisions. We should be developing methodologies to check the models, and we must have explainable AI. If you work inside of a company, graduate students, and you make a model, and nobody can understand it, is anybody going to use it? Nobody will use it. What happens if your models don't get used? No, I don't want to be negative. What happens if your models get used? Turkey for Christmas. That's when you get the bonus. That's when you get all the great opportunities. And that's what I want for you. Stationarity. Stationarity remains as a dragon to be slain. Anybody ever have troubles with stationarity? Stationarity is a big deal. In geostats, we talk a lot about it. Ordinary kriging relaxes the stationarity and the mean. We know that, but we still have the stationarity and the varogram and all that. What is non-stationarity? Well, I'll tell you what it's not. It's not this right here, non-stationary. This is going to be a nice stationary image, stationary statistics. This is an example of non-stationarity right here, these three. This is a case where we have a long varogram range relative to the model size. That can create a non-stationarity. Another thing that can happen is we can have this case right here. What we have is a trend plus a residual, a stationary residual, but we also have a trend, and the superposition of the two creates this non-stationarity. And this right here, do you see it? Two separate populations brought together. Artificially, I know it's a vertical line, but you can see, in fact, that that's non-stationary. And so the question is, how do our machine learning, deep learning models perform in the presence of non-stationarity? Do you think they just take care of it? Do you think they're able to work with non-stationarity? How do we detect non-stationarity? There's been a lot of good work on this. I do not walk away from the point that stationarity is a decision, not a hypothesis. It can't be proven. I do agree with that. But if you accept that, there's still methodologies like Julian Salazar had some work that extended the bootstrap methodology of journal to test for stationarity, which was really cool. And of course, Dr. Boisvert over in University of Alberta was doing some really nice statistical testing using shifts in order to go ahead and test for non-stationarity. What are the cases of stationarity within deep learning? How do machine learning models treat stationarity or non-stationarity? What do we know? And what we know specifically, that a lot of people take predictive machine learning models and they just do this. They take the data set as if it's not spatial. I'm looking around the room, I know we all do it. We remove the X and Y, and we go ahead and we just make predictions using all of the predictor features for the response at all locations, assuming stationarity of the model. Everybody agree with that? It happens a lot. The X and Y's disappear. That is a very strong assumption of stationarity. Anybody here work with convolutional neural nets? Anybody ever look at your kernels? Do you ever look at them? It's cool, isn't it? You can actually see sometimes the edge detection, gradient detection. Sometimes they are meaningful. You bet they are. I think they're really cool to look at. But guess what? Do we assume stationarity of the kernel? Those weights are going to be constant over the image. Everybody understand that? And so that's a pretty strong stationarity assumption. Also, have you ever used layers that do pooling or stride to reduce dimensionality? In convolutional neural nets, what is that doing? It's creating location and variance. In other words, when they're detecting the dog in the image, they don't want it to matter where the dog is. You see that? That is an assumption of stationarity. Conditional GANs can impose local information. There are ways that we can get around this stationarity assumption. What happens if you pose a very simple experiment? Let me make a simple prediction with a convolutional neural net, and I will turn a dial, increasing the level of non-stationarity. How will it perform? This is the answer right here. Convolutional neural net, error right here. Look what happens. This is stationary. This is becoming more and more non-stationary. What happens to my error? Boom. It has a lot of trouble with non-stationarity. And don't even get me started about mixing populations. It doesn't do what you think it's going to do. What happens if you use a methodology? Anybody here familiar with transformers? Anybody using ChatGPT to do your coding? It works pretty good, doesn't it? I'll tell you, it can speed things up. What we did is we used SwinT, a transformer specifically designed to work with images. It uses shifted windows in order to make it more practical. And what we did was when we used the methodology that was able to account for non-stationarity, aka attention mechanisms and locality encoding, they were then able to do a much better job with non-stationarity being present. Okay, so what are we learning? Just like ordinary kriging, we need to recognize the degrees of the decision of non-stationarity or stationarity implicit to the method. We have to understand the assumptions of non-stationarity or stationarity within our deep learning methodologies. We know about that. What about working in a new space? Anybody else agree that Gaussian space is a happy place? I love Gaussian space, low parameterization, everything is so understandable, so many of our theorems work. If you work in Gaussian space, I think we all do. If you've done any sequential Gaussian simulation recently, it's all in Gaussian space. What's the benefit of that? If you're in Gaussian space, all the local distributions are known from just two parameters, the Kriging estimate and the Kriging variance, right? It's very useful to have that. The global distribution is reproduced on back transformation because when you take a bunch of draws from Gaussian distributions and you put them together, they're Gaussian too. And the back transformation works out and everything's fine, and we have simple parametric representations of multivariate relationships. So that's really, really nice for us. Anybody ever work in latent feature space or in other dimensionality reduced spaces? It's really exciting because machine learning is getting us to think about a lot of different spaces we can work in. Once again, Ashid and Pyrcz had the work where they were looking at representing uncertainty models by looking at MDS. They went further and they were doing classification of training image patterns later on. And Mabadeje, here in the audience, was working on analog identification using this low-dimensional representation of MDS. In fact, she went one step further and she stabilized the space. Am I stealing your thunder from your talk? Okay, I'm sorry if I am. And what she was able to do was actually look at what would happen sensitivity in this space. If you vary some of the parameters of the model, you can actually see your example move through the space. You can actually find analogs doing this. A student of mine, Honggong Jo, my very first PhD student, who's now a professor in South Korea, saw some friends of his here, that's very nice. What he did was he went ahead and said, we'll do ensemble Kalman filtering. You know that whole thing about forecast and assimilation updating, forecast updating, those cycles? But instead of tuning all of the permeability values in your million cell model or a large number of permeability values, why don't we go ahead and just tune the latent features for your GAN? And what's really interesting about that is once you train your GAN with the discriminator, learning the loss function, your GAN will always make realistic geologic models. If you ever run ensemble Kalman filtering, you'll find that it commonly will blur your heterogeneity. It will commonly wipe out your shale drapes and your conduits, your high permeability conduits. And so what happens is if we work with ensemble Kalman filtering on the latent vector, it's lower dimensionality, and all of the models remain geologically feasible as you match production data. And so what's it look like? It's really exciting. Here's an example using the ensemble Kalman filtering supported by GANs. Here's traditional ensemble Kalman filtering. And if you look at the models here, they preserve the shale drapes, the blue lines. They preserve the lobe geometries. You see the results with the standard ensemble Kalman filtering, and you, in fact, have lost a lot of the structure. What does it behave like in flow simulation and forecasting? Here we go. We got the reference line, the red. This is with the deep learning approach in the latent feature space, and this is outside that space, and you can see significant reduction in uncertainty and bias. It has high precision, but sometimes low accuracy. It's getting it wrong. It's losing the geology. Okay, so stabilized MDS space is really exciting because we can start to do all kinds of calculations and visualizations in that space. Latent feature space is really, really cool. I get really excited about autoencoders and opportunities to work in this low dimensional space. All right, I got time for can I just do one more? Can I just do one more and I promise I'll be done? Okay, I'll try to keep my promise. Hierarchical modeling. Is geology hierarchical? Do we ever build a model just at one scale? Do we ever have arguments over what to call the different scales? Anybody ever been in a geologic argument about architecture and hierarchies? I see some laughing here. I was in a PhD defense in geology in UT, and I saw that argument for about half an hour. Okay, so here we go. We got different types of structures at different scales. We got slope valley fills, we got lobes, we got bedding within the lobes, we got lobes within lobes, we got lobes, we got channels within channels within channels. What do we do? How do we capture that in our models? Has anybody here ever used the cookie cutter approach to build multi-scale models? How do you do that? You go ahead and you model the thing at the large scale, shown with this indicator-based model, or it might have been a truncated Gaussian model. And then what you do is you go ahead and you model within each one of those things, but what you've actually done is you model over all the space for the yellow, and then you cut out the part that was black, and you put the black model in there. You see what I'm saying? It's the cookie cutter approach. Can everybody see the problem with it? You have inconsistency between the boundary outline and the fill. Is that a multi-scale model, or are we just fooling ourselves? We're losing valuable information. Now, anybody here saying, well, but I can do a lot with trends, locally variable azimuths, secondary features to improve this? Yes, you can. Is it going to be perfect? No, it won't be. You see this model right here, this object-based model? We have channels that are popping out through the bottom of the model. They're not confined to the slope valley. Look at what happens if you use Pyrcz. Anybody ever try this stuff out? You can go online to this website right here, and you can try out Pyrcz. They'll give you a default outline of a cat. Okay, now what you do is you hit generate, and it will fill in the cat inside your outline. Do you see the magic here? You see what we can do? We want to treat our multi-scale problem like this Pyrcz problem. Now, warning, if anybody here is a bad drawer, and you go to this website and you try to sketch a cat, and you're not good at sketching cats, get ready for nightmare fuel. Because what you're going to see is a pile of hair and whiskers and eyes in the wrong locations. Please don't do it. I warned you, okay? But go ahead and fill in the details. We can do the same thing in our subsurface. We can sketch or use the geometries from the larger scale from the lower resolution data, and we can use Pyrcz types methodologies for super resolution to basically put in details inside of the geometry. In fact, my student developed a methodology called stochastic Pyrcz because this Pyrcz approach is really a conditional GAN that uses a new L1 for local accuracy. And the problem is it becomes too deterministic. And so what he did was he relaxed that so it became more stochastic, so we have uncertainty models. But now these models span multiple scales, and at every scale they're consistent with each other, which I think is really, really cool. Multi-scale models. Okay, you remember that part where I said I promised just one more? Can't do one more? I knew I was going to do that. I'm sorry. I try to be honest. But this is it, and I promise I'm finished. Uncertainty modeling. What I tell my students, I tell everybody, it's more important in the subsurface to have a good uncertainty model than to have one best estimate. Who agrees? Uncertainty is much more critical. Thank you very much for your support. I appreciate that. I agree. How do we build these uncertainty models? We're good at this. We'll hear this at the conference over and over again. Kriging gives you an uncertainty model at locations, frequentist and Bayesian probability frameworks, bootstrap and Monte Carlo simulation, realization scenarios, and so forth. We do all of this. We build these models. Now what we do is when we work with sequential Gaussian simulation, we know, and we're kind of proud of this, that you can show by recursive application of Bayes' theorem, you can actually solve for that joint probability, I mean that high order joint probability, 1 million cells, by sequentially simulating, expanding these conditional probabilities. That's the sequential paradigm. What does that mean? It means that sequential Gaussian simulation under its assumptions is correct. It is a sampling of the joint distribution. It is an uncertainty model. Okay, everybody hear that? Everybody good with that? We're cool? Okay, now, what about machine learning? Is machine learning a sampling from an uncertainty distribution? How did you build it? Do you remember this part of the talk? It was my favorite slide. I'll be hurt if you don't. It was a really good part of the talk, right? We build these models that are tuned to have the right complexity so they're not overfit. Has anybody ever played with k-means clustering? Has anybody ever looked at the solution scheme? You know what they call that? They call it a heuristic. What is the solution space for k-means clustering? What's the combinatorial? K to the n. K is the number of categories, n, the exponent, is the number of data values. Is that a big solution space? You bet. How do they solve it? They randomly seed K prototypes. They assign data to the prototypes. They correct the prototypes. They iterate until it converges. The original paper in K-means clustering says, we promise this will give you a minimum. They didn't say global minimum. They said it will give you a minimum. That's what they promised. That's the only thing it says in the fine print. Let's go ahead and look at K-means clustering. Here's an example. I took 3K. I took a data set that is a little bit ambiguous. It doesn't have 3 clear clusters, right? Is this sampling an uncertainty distribution? Here's one of the models. Does this look good? How about this model? How about that model? Well, all I did was just randomly perturb it. Guess what I did? I made a dashboard for this. I tell you, it's a problem. I need help. I really like making these dashboards. But what I also did was I formulated the CDF of all of the different loss function, which they call inertia. Inertia is the loss function for K-means clustering. And what do you find? Does everybody see that? You know what that is? Watch. Everybody see? That solution right there. Do you see how it's different? Let me go back again. This was the other previous solutions, and then that one. That's a local minimum. And it happens 5% of the time if I repeat this exercise many times. Is this an uncertainty model? Or is this an artifact of the heuristic of K-means clustering? I suggest this as an artifact. It's not an uncertainty model. How do you test if you have a good uncertainty model? I'm out of time. I'm going to finish, I promise. Okay. Deutsch has a methodology called uncertainty goodness. And what you produce is the accuracy plot and actually checks for uncertainty model goodness. What we propose is that you can use the general framework and you can run it on your machine learning model ensembles. One of my students did this. Eduardo Maldonado Cruz, happily working at Chevron now, ran it. Look at that cross-validation plot. Does it look good? Look at the accuracy plot. The accuracy plot says you had good estimates, but your uncertainty model is terrible. It's awful. It's inaccurate and imprecise. Look what happens if you include Deutsch's model goodness for uncertainty in your loss function for your machine learning model. You get good estimates, and you now have an ensemble that has pretty good uncertainty. We can start building machine learning models that have good uncertainty in them because they lack that statistical pedigree to be able to know that they have a good model. Okay, I'm going to finish. Let's think about uncertainty. Let's not fall into the trap of only thinking about the most accurate estimate. Concluding remarks. I'm excited. In fact, I'd like to say I'm stoked. I'm stoked for all of us in geostatistics. I think there's a lot of opportunities. We are further down the path into the adoption of the machine learning and the data analytics type of approaches. Geostatistics and the science of geostats will continue to lead these developments and to share our experience with our brothers and sisters in our community. And all of the things we know that we're really good at, they're very powerful. They're things that we can apply within the fourth paradigm that everyone's using right now. Okay. I have a lot of educational content. I already confessed that. Check out my GitHub account, my YouTube channel. I share all of my educational content from UT. And let me know if it helps you in your classes. I hope it does. Thank you.
Thanks a lot. We have time for a few questions. Want to go first, Vasily?
Thank you. Thank you, Michael. Great talk. Lots of questions. For the sake of time, just ask one, following up on the uncertainty argument. Just try to open the debate here about the precision. Yeah, that one's great. Yeah. So do you really want to be accurate and precise? Because where I'm coming from, I'll share the accuracy, but I'll go easy on precision. So I don't want to be precise. So what's your take on that? Thank you.
And it's a really good question. You know, it's that old case of going into your manager's office and they ask you, how big is the reservoir? And we could walk into the office and we could say anything between a 0 and a billion barrels of oil. And of course, that's a model that it's going to be accurate. We're not wrong. We're not biased, but it's not useful. And so when I'm talking about precision, I'm talking about if we're above this line, what it means is we have a model where our uncertainty distributions are too wide. In fact, the uncertainty distributions could be cut down and we could get a useful model that's accurate and precise. Now, at the same time, I'm going to just acknowledge this. Any type of methodology like this for uncertainty model checking is going to be fundamentally a cross-validation approach where you're withholding data. And we've got a big question to ask. Is that a fair way to test the uncertainty model? Is the way we're testing as difficult or as complicated as the actual use of the model in real world? So I agree, there's a lot of debates we can have about exactly are we testing the uncertainty model. Thank you.
One more maybe before a coffee break?
Sorry, I ran into coffee.
Hi, thank you for the nice talk. Is it working? Yes. I have actually a doubt about machine learning models. How sensitive are they to the scale of the data? Because there is an underlying assumption about absolute scale in all the methods I've seen. Yeah. And you know, I work in compositional data and we work in a different scale.
That is a wonderful question. I really appreciate that. I really omitted talking anything about that. And I'll tell you what people do in machine learning is they often take their data, they collapse it into a multivariate table. They got their pandas data, it's tidy in R, it looks really good. It's features and samples. And nobody pays attention to the fact that we have totally different scales between the different features, between the different measures. But we in the geostatistics community, we've known that there's ways to cope with that. I go into like really high-tech areas, meeting with like really technical people, and I start to explain the concept of volume variance and scale, and I start talking about, how that impacts estimation. I ask the question, what's harder to estimate? A teaspoon of the subsurface, a cubic centimeter, or the size of this room? And they always get it wrong. They always think it's easier to estimate that teaspoon. You see what I'm saying? They don't understand volume variance relations. And so what I say is that we're the bearers of that light. We should take that to the rest of the community because we think about uncertainty, scale, spatial continuity, and so forth. That's been part of our history, right? Yes, it's a big problem. I had some students look at scale effects. Yes, and we know it will be, just like in geostats. Thank you.